This is the Berkeley Statistical Computing Facility Workshop Day 2, Friday, November 14th at UC Berkeley. Okay, so let's see. So what I was saying was the main things I thought I would talk about today are doing a basic simulation sort of massively in parallel, and then do a bunch of examples of fitting statistical models, so basically optimization. And a couple caveats or just sort of comments on that. Sort of what I'll show is just sort of a few different examples of optimization algorithms. They're not necessarily the best optimization algorithms for any given big data set you need to optimize. That's something I've been learning a little bit about, but I'm certainly not an expert on that. So I'll show you a few examples, and then we might want to open it up for a little bit of discussion to see if there are people in the room. There may be people in the room who know a lot more about optimization with large data sets, and we can talk some about that. So please do jump in if you have comments or can add into the discussion. Okay, so let's start off with I'm on section 2.4.3 of the HTML, and this is basically just an example of suppose you had a huge data set and all you wanted to do was basically subset it into a number of smaller chunks, and each of those smaller chunks was small enough that you could work with it on a single machine. So there's not really a great way to do that in parallel, but this is just an example of doing that where we're basically going to set up key value pairs. So each observation is going to get mapped via a map step such that we have a key and then the value associated with that key. And then we're just going to basically filter sequentially on each of the keys. But in each of those filtering steps is going to be done in parallel across the entire data set. So I just have my create key value function here, which takes my input line. And remember, these lines are this airline data set where each line is just basically a text string that is a comma delimited set of information on a given flight from one airport to another. So it's still basically as a text string. So my function that does the creation of the key value pairs has to split up that observation by the comma delimiter. It's creating a key, which I think in this case might be the departure airport. That's the 17th field, since Python is 0 index, and then it's returning the key, and then the value is just the original line. Okay. So I'm doing a Spark map with that function on the original lines data set, and then I'm caching it, so I'm saving it in memory because I'm gonna use it in a minute. And then in this case, there are probably more efficient ways to do this, but I'm doing a count by key, and then I'm applying this keys method to it to basically return the unique keys, which are going to be the unique departure airports. You might, if you were working with this data set, already have that as sort of a separate piece of information, some small dimensional just list of the airports. So this would be sort of a roundabout sort of calculation-intensive way to get it, but just for the sake of illustration. And then all I'm doing here is sort of what you might expect, which is I'm just looping through each of the different unique keys, and I'm going to create a string that's just going to be the file name for each of my subsets. And then I'm doing a filter, which we saw last time, using an anonymous function to say, is the key value for the given observation, which is going to be, so we've got the key and the value, and so x of 0 is going to be the key for any key value pair. So is that, for a given observation, is that key equal to whatever the cur key is that I'm currently trying to pull out the observations for that key? And then in this case, I'm doing another map where I basically just throw away the keys because I decided I just want to keep the values because the keys were just for the purpose of doing the subsetting. So that second map is just basically throwing the keys out. You wouldn't necessarily have to do that. And then, as we talked about last time, now I'm doing a repartition of 1 so that I basically collect all of the information for a given key on a single node, so it's in a single file on a single on the disk on a single one of the nodes. Okay, and that way, when I then copy it back from the HDFS to the master node, if I were then going to use it somewhere else, it's all just a single file, and I don't have to worry about concatenating it separately outside of Spark. Yeah, Daniel?
Just a quick question about the broadcast. I do understand how it provides that variable to all the worker nodes, but my question is actually about the return value. And you, in several cases, use it a couple times and save them as different values.
Yeah, I think all that's doing is just basically giving you some information about whether it succeeded. Do you want to say anything else about that? This is
The
our resident
return-
expert for
the
this.
return value of the broadcast call.
Yeah.
Yeah, so that just gives Spark a handle on the remote. Like, so that essentially gives Spark a symbolic handle to it on the remote hosts. So then, like remotely, when you use it, you'll say, with that broadcast variable, I want to get the value, and locally, like locally on each executor, Spark in the background will take care of making sure that value is available.
Right. So you're talking about the const.
Exactly. Yeah. So const is essentially like a handle that Spark uses to make sure that everybody gets to get the broadcast value.
Is there anything we would possibly do with it in doing something like this?
Right here, not necessarily. No, I don't think so. Because I guess, can you scroll the rest of the line?
Yeah, I'm not doing anything here, except I'm just not anything germane to this discussion. Okay, yeah, so I'm repartitioning, then I'm saving it out as a text file into the HDFS, and then if I wanted to go grab it and bring it back to the master and take it wherever I wanted to, I could do that. Okay, so that's that. So the next thing that was sort of a holdover a little bit from last time. So let me talk a little bit about simulation. So this is this calculation that is a Monte Carlo estimate of the value of pi. So obviously kind of a silly example, but this is in the Spark documentation. And I realized after I sort of put this in my demo here that in reality lots of simulations are fairly simple, and so a lot of things could actually fall into this. It wouldn't be all that hard to take this code and make it into any other simulation that you want, and sort of make it a little bit more, it might become a little more complicated, but it would fall into this sort of way of doing things. So I think it's a nice little example. Okay, so the idea here is I wanted basically to generate, to figure out the value of pi, I'm going to generate a whole bunch of random two-dimensional vectors. And those are going to be in the unit square, and then I'm going to see how many of those are inside the unit circle, and then I can do a simple calculation to determine pi from that. So, if you're thinking about this, you think, oh well, maybe you could potentially, if you were writing this in a way that wasn't optimal, you could basically have one partition for every random vector that you generate, and you could try and make millions or billions of these partitions. But that's not going to be a very efficient way to do this. The efficient way to do this is basically to make a modest number of partitions like we saw last time and have each partition do this calculation for a relatively large number of these random two-dimensional vectors. So in order to basically generate many, many of these random two-dimensional vectors, I'm going to do that in chunks so that each partition does a piece of that. And then I'm going to sum up the total number of those two-dimensional vectors that are in the unit circle on one partition, sum it up on another partition, and then do a grand sum across all of that. So that in words is what I'm doing here. So the samples per slice, maybe I should have written samples per partition, but when I say slice here, I basically mean partition. I'm saying, okay, generate 1 million of these random two-dimensional vectors for each of my partitions. And in this case, I decided to take the number of cores that I have on my cluster, which is 12 slaves times 2 cores per slave. I'm going to have 480 processes here, so 480 partitions, one process per partition. In reality, actually, why don't we run this? But I think I'm going to do this with somewhat fewer, just for the sake of time here. So I've already started up Spark. I've already sort of run a bunch of this, so I may rely on some objects that I already have existing in here, but so here I'm going to have 5 times 24, so I should have 120 tasks that I'm doing, and 1 million each one, so this should be doing 24 million of these random vectors. And so the function that I'm going to, well, let me step ahead first here. So basically, to do this, I don't yet have a data set that is sitting in these partitions yet, so I'm going to create a very simple distributed data set. I'm just going to distribute the numbers 0 up through 1 minus the number of processes that I want to run. Okay? So that's what xrange. Xrange is just creating 0, 1, 2 up through 119, so 120 processes. And then parallelize is basically creating the distributed data set where it's basically distributing out one of these 120 numbers out to each process. So this is basically this parallelize step is basically going to create my RDD, my resilient distributed data set. So then I'm going to do my map step, And so I'm going to use this sample function. And since the value coming in is the number 0 up through 119, I'm going to set a separate seed for each one of the processes. And then for each one of these processes or tasks, I'm going to generate 1,000,000 of these random x's and 1,000,000 of these random y's. And then I'm going to return back the number of them where the length of the vector is less than 1. So I'm going to do that in parallel across the 120 processes. And then my reduction step is just going to be an add. I'm just going to sum across the, so I'm already doing a sub sum here, and then the reduction step is summing across the partitions of those partial sums. Okay, so if I do that, we'll go ahead and get that started here. Hopefully that won't take too long. Okay, so you can see it's already churned through the first 24, it's already churned through the first 24 of those processes. Now it's up to 48 out of the 120, et cetera, et cetera. It'll finish pretty quickly. And then my calculation of pi is just this simple 4 times the total sum divided by the number of samples that I did. Okay, so that just took a few seconds, and I get that pi is 3.141. And then then the approximation is not so great. It's just a Monte Carlo approximation that in this case only goes out to a few digits. So obviously this is not too interesting from a substantive perspective, but it seems like you could basically take this and do any sort of simple simulation that you wanted to across many replicates. Okay. Any questions about that or comments? Let's see. Yeah, when I was first playing around with this, I didn't realize this bit about you couldn't create too many of these parallel tasks, and I tried just basically creating one per random vector, and I got up to about 50 million, and then it crashed because I had too many tasks. And it didn't crash; it just basically hung. So it can only handle a certain number of maximum number of partitions. Okay, a little bit about random number generation. Those of you who've seen me talk either in 243 or in other parallelization contexts have heard me talk about random number generation, that you want to make sure that in many simulations it's important to make sure that you don't have any overlap between the random numbers being generated on one process and the random numbers generated on another process. I don't know of any way to do that to ensure that in Python, so basically what I just did here is basically hoping that when I set different seeds, that the random number, the subsequence of random numbers that I get are distinct subsequences and don't overlap. I don't think there's any guarantee of that, but unless you're doing some huge number of random numbers, I don't think it's too dangerous. Okay, and then one comment here. So far, everything we've been doing has been interactive in the Python session. And so you can, of course, do any of this in batch. And so I just have an example with the calculation of pi where we can do it in batch. So I created a file called pycalc.py. It's in the repository. And it's basically just the code that I had for doing the pi calculation that we just saw a minute ago, except I also have to import Spark context from the PySpark Python module. And then I have the line that says, this is basically a Python program that we're going to run from the command line. And then I have some checking where I make sure that the number of input arguments coming into my Python script is the appropriate number of input arguments. So that's this business with sys.argv. And then basically the way this program is going to get invoked is I'll run spark submit. I'll give it the name of this Python script here, and then it's going to take 2 arguments, which is the total number of samples and then the number of slices that I want to use, the number of partitions or processes that I want to use for the processing. And so then I programmatically assign that into the total samples and the number of slices. I figure out how many samples per partition or per slice just by doing the division, and then I have the same thing that I had before. Okay. So let's see. Yeah, so then basically you just run it in the way that I already indicated. So it's pretty straightforward.
Just
Yeah.
one question, because I was like, what is this SC defined before? maybe I missed it, but here I saw that you actually assigned it to this context. Did you also had that before? I was kind of wondering before where the SC came from. Like,
Yeah, so the SC before is all set up for you by running PySpark.
I see.
And then the difference between, in some sense, part of I'm sure there's more going on, but part of the difference between just running Python and running PySpark is PySpark will set up some of this for
I
you,
see, I
including
see.
this SC object. If you're running this as just a Python script in batch mode, then you need to instantiate this SC object that has all the information about the Spark cluster.
Oh.
Yeah. It's basically a handle on that. Yeah.
Is there like an IPython access, like interactive mode kind of thing?
Yeah, that's a really good question. And one thing,
PySpark or something?
yeah, every so often I was wondering as I was doing this, and I wanted to do like tab completion and stuff. So I was like, oh, could I have just used IPython? And I was busy enough and didn't get around to ever figuring it out. Is there? Can you use
I do
IPython?
believe that there is a hook in. I haven't used it before, but yeah, there's actually someone using it earlier today who was using an IPython PySpark connection. Let me see if I can get more information. I'll send it to you.
Great. Yeah. So if he sends something to me, then I can put it up on the workshop website.
I think you can just call this Python.
Yeah, presumably you could just start IPython and then manually set up this Spark context object, and I would guess that would work. Yeah.
I was wondering, so I mean, you can specify how many slices or partitions or whatever, but I guess, like, think about that. Is that, I mean, so you can definitely manage that, but because I see that as analogous to, like, with low-level programming you do, like, you can manage memory or whatever, but what's the purpose of it here? Like, do you really
So I mean,
care about
yeah, I mean, you definitely care. This goes back to some things we talked about last time, which is that you in terms of load balancing and making sure all of the worker CPUs are busy all of the time, and that you don't have one of them taking a long time and then 4 being idle. You want to have at least as many partitions as there are CPUs in your cluster, and generally, I think the rule of thumb is you want something like 2 to 4 partitions per CPU.
Yeah.
And the idea is to do some load balancing based on that. But you don't want too many, because then you start breaking up your data set into small pieces, and there's just a lot of overhead involved.
Okay, I guess I was wondering why that's not just abstracted and somebody hasn't figured out a way to optimize that. But
Yeah, I don't know. It may just be that for different problems, you want to play around with it and try different numbers of partitions. Yeah.
okay.
Okay, so let's move on and talk about some different ways of fitting models. So I'm going to go through a regression example in a couple ways. I'll talk about regression just using the sufficient statistics and just getting the usual OLS estimator or the MLE. I'll talk about doing coordinate descent, and I'll talk about gradient descent and a little bit of lasso fitting, which also in this case I'm going to use a coordinate descent method. Okay, so suppose this is going to be basically a very sort of tall, skinny design matrix in regression. So we have a really, really large number of observations, but the number of covariates is not too big. And the reason is what I'm going to do here to do the regression is I just want to compute x transpose x, and I want to compute x transpose y, and I want x transpose x to not be so big that it can't basically be brought back to the master and then manipulated on the master. So my rule of thumb here was roughly, well, let me make sure p is not any bigger than, say, 5,000. If p is around 5,000, the x transpose x object would be something like 200 megabytes. So that's not getting to be too big. But if I start to get p up to 50,000 or bigger, 10,000, 20,000, 50,000, I would start using up a huge amount of memory just to store this, to have this x transpose x object in memory, and I would have trouble collecting it back to the master. Even indeed, I would have trouble working with a given component of x transpose x on one of the on any given worker. Okay, so what do we need to do? Well, if I'm just thinking about this as in parallel, working through every row of my design matrix, every row of my matrix of observations by predictors, well, then x transpose x is just the outer product of every one of those individual observation vectors, and then I sum up. I basically, for each observation, I get a matrix, and then I'm summing across the matrices element-wise, and that's what x transpose x is. And analogously, I've got a vector from x times the scalar value yi. So what I've done here is I've basically, I'm first doing a filtering step where I take my original data set of the raw CSV input lines, and I need to basically filter out places where I have missing values, and I need to filter out the header rows because the header rows are still in there because it's just the raw text from the CSVs. So that's what this screen function is going to do. So I'm going to, I've already done this, so I won't actually run this, but I'm going to create my lines RDD by reading from the data airline directory on the HDFS. I'm going to filter it using the screening function. So I filter it down, I filter out the missing values and whatnot. Then I'm going to do my repartition to create 192 partitions, and then I'm going to cache that, and then I'm going to go ahead and work with that. And so all that I need to do to create X transpose X and X transpose Y is I have a cross product function that's going to bring in a line. In this case, I'm going to do a regression where I'm going to regress the departure. Oh, the other thing I did here, this is not a good regression, but so don't think about this as good statistical practice. But this has the observations have a very, very long right tail because I could have delays that are like 12 hours or a day or things like that. So I'm filtering out any delays that are less than minus 30 minutes, so where the plane supposedly left more than 30 minutes before it was scheduled to leave. And I'm filtering out anything bigger than more than 12 hours of delays because I don't want to deal with the tail. So obviously if you were really doing this, you might be thinking about log transforms, you might be thinking about running a logistic regression on delays more than a certain amount of time, but just for the sake of an illustration here, I'm just going to regress directly on the departure delay, having excluded both tails. Okay, so the regression I'm going to fit is I'm going to regress on the distance that the plane traveled, that the flight is, and I'm going to regress on the day of the week, and that's all. So obviously there's lots more things I could do in this regression. This is not all that interesting regression, but just for the sake of doing an example, this is the regression I'm going to do.
Day of the week, is this the numeric value day of the week, or is it like the binary day of the week?
Yeah, so that's a good question. The day of the week comes in just as a number of 1 through 7. And I'm gonna manually create my design matrix where I have dummy variables for 6 days with an intercept. Yeah. Yep. So that's what I'm doing here. Remember the line comes in as text. I'm splitting it up. I'm converting to numeric values. So the y is going to be the 15th field, which is the departure delay. The distance is the 19th field. The day of the week is the 4th field. And then I'm basically going to create an x vector for each observation where I fill in an intercept column, the distance column, and then this is dealing with the dummy variables for the day of the week. Okay. And then I'm going to do an outer product. I'm also going to do the X transpose Y, and I'm going to basically bind the X transpose X matrix together with the column that contains X transpose Y. So I'm going to bring back the two sufficient statistics in a single object. And so what do I then need to do to fit my regression? I just need to take my original lines data set. I need to map from that to the cross-product matrix information. And I need to do a reduction where I add across all the observations. And then now I'll have the sufficient statistics object back at the master, and I can just do the usual linear algebra that I would do to solve the system of equations X transpose X inverse times X transpose Y, pulling out the pieces that I need from this sufficient statistics object. Okay, so if you did that on the entire airline data set, not just the 3 years that I've loaded in here, but the 1987 up through 2008, it takes about 11 minutes. And part of the reason it takes so long is because I'm basically working through each row and doing an outer product of doing the linear algebra row by row. And that's not very efficient. There's a lot of overhead in basically calling the linear algebra routines the 120 million different times. So the smarter thing to do is to use this map partitions function, and basically what this is going to do is I'm going to take each partition has a large number of these rows of observations. I'm basically going to map from all of those rows, and I'm going to map it into a single matrix for each partition. And then with that single matrix, I'm going to do X transpose X and X transpose Y. So now what I'm doing is, instead of doing a sum across all of the observations, K is going to index across partitions. I'm going to get a submatrix X sub K, and I'm going to do the sufficient statistics on that submatrix. So you can think of this as, I've got my original X matrix, N is very large here. I'm basically taking each partition and I'm basically creating this submatrix here. And then I'm going to do the X transpose K, XK, and the X transpose K, X transpose K, YK in pieces here.
So in order to do that, you have to duplicate the whole data set in memory, presumably, right? I mean, because the output of this read point batch thing is going to be
Another one of these
copy
data
of your
sets.
thing, but broken up into partitions. Is there an alternative way where you could just tell it, please don't process my data row by row, but process it in larger natural chunks without creating a duplicate intermediate product?
I don't know. I mean, I think what I need to do here is I need to basically create a representation of the matrix that I can feed into the linear algebra routine.
Yeah.
So I don't know if there's any way to do that without explicitly creating the NumPy array.
The reason I ask is it does exist, right? I mean, it has been partitioned, it's in memory across a certain finite
Right.
number of workers, and if you could just access that directly, then you could do this without this intermediate
Right.
step, right?
Yeah, so there are folks who are working on that right now. Yeah, so it's like ultimately the distributed linear algebra and data distribution is a surprisingly difficult problem. So there are people who are working on this right now who are working with the scientific computing folks who have done a lot of the like high performance computing. So they're trying to resolve that problem to minimize data duplication. But right now this is the approach that a lot of people are using. So yeah, because it's ultimately it's like when the data so like even though the data exists twice right now, it may exist on different nodes, right? For example, this partition 1, partition let's say like your final partition is 20. Let's say they may be on different computers. So even though that data does exist, both are not locally in the same place necessarily.
But in this case, I'm just taking the partition, which is on one node, and I'm just reformulating it on that same node.
Yeah.
So it's not like I'm doing any shuffling across nodes. I'm just doing some work on each node to get it in a more convenient form for the linear algebra.
It is partitioned row-wise, right? It's not that you have,
Right.
so-
All I'm saying is it's already been partitioned, and a subset of the rows belong to our partition, and those all sit on one machine.
Yeah. So, yeah, I think that's like a response to what you just said.
Oh,
I was
I
responding to your comment
Oh, okay. Yeah,
and
so
not to
you want-
yours.
I
Yeah.
wanted to do a response.
No, sorry.
Okay.
Okay, so I did just run this. This is just the 1987, 1988, 1989 flights, so it's not too surprising that this finished quickly. And in this case, I guess I did partition to 192 in this case. So it took about 6 seconds. Sufficient Stats 2 looks exactly like Sufficient Stats from the original one where I didn't do the map partitions, but here instead of doing lines.map, I did lines.map partitions, and I used this read point batch function. And so what that did was map partitions is basically going to create this iteratable object that gets fed in as the argument to the function. So I can now iterate through this iterable object, which I've converted to a list. I'm going to iterate through, and for each row, basically for each line, I'm going to create my my x vector, which contains the elements of the x matrix for that observation, and I'm going to let's see here. So the y observation is actually the 0th element of this vector, so I haven't sort of it's all sort of glommed together there. So I'm basically doing the x row, tacking on the y, and doing the cross product of that entire vector. And then I'm saying, okay, I created a matrix up earlier here, and this is saying that the ith row of the matrix should be this x vector. So it's setting up this single NumPy array, and then I'm explicitly doing this, the xk transpose xk and the xk transpose yk, by doing matrix transpose dot product with itself. Okay, so that's doing all of these calculations. And then I can just pull out from Sufficient Stats 2, I can pull out the x transpose x portion, and I can pull out the x transpose y portion, and I'm ignoring that there's another row that's also x transpose y transposed, and that there's a sum of the yi squareds down in the corner, I guess in the upper corner of the matrix. But I'm just pulling out the pieces that I need. Actually, maybe I can ask our expert here. I realized as I was playing around with this that I needed to return this as a matrix within a list. Is that just a standard Spark thing that the elements of an RDD have to be a list,
Well, so when you do a map partitions, it gives you a list and expects back a list.
Okay.
So
Okay. Yeah, so there's just a syntax thing that this is the sort of thing that could throw you off easily if you don't see this. Inside the square brackets, I'm just creating a NumPy array, but I'm returning it as a single element list that contains that NumPy array, and that's what the square brackets are doing here. Okay, yeah.
So you just use linear algebra in NumPy to calculate X transpose X.
Yep.
This one, yeah.
Yeah.
And that should be faster.
That should be fast. It's just Python should just call whatever linear algebra, whatever, in this case it's probably just a BLAS routine, whatever BLAS routine is on the system that it's linked to. But you would actually, if you were doing this, you'd want to make sure that the BLAS, and if you're doing any of the linear algebra factorizations, you want to make sure, I guess it's more relevant is the BLAS. You'd want to make sure you have a fast BLAS installed on the cluster that you're running. Yeah. And that can make a big difference as usual. Okay, other questions or comments?
It's just a general Spark thing, but when I was talking about partitions and then the numbers and all that involved, is there some sort of abstracted mode or like a default that'll just figure out and
just the number of partitions to use? Or?
Yeah, just
Yeah.
all those kind of settings.
So when you actually load data from disk, like if you have a file that's sitting on disk and you're not using the sc.parallelize, then yeah, that'll, like what happens is you have this input format that it uses to read data off disk, and it'll say, I can split the data, you might say, oh, I want this many partitions, or you may not even give it any guidance, but
Yeah.
it'll say, hey, I can split the file into this many partitions, and it'll find where to split the file, and we'll handle all of that for
Okay.
you. Additionally, if you...
But by default, my understanding is, for example, with the airline data set, there are 22 input files, one per year, and it basically just made 22 partitions out of
Exactly.
that. That's the default. That would be the default. Okay.
Yeah. Yeah,
So that might not be the smartest
partition.
partitioning, particularly if the files are different sizes.
Yeah. But for some of the input file or some of the input formats can handle that better than others. I don't know about the one that you're using right here off the top of my head, but yeah, it may be able to.
Okay, so the next thing I thought I'd do is just show you coordinate descent. It's not clear to me that this is really realistic, but I thought it would be a useful thing to show, and maybe people will have some suggestions here. But so if P gets really big, the problem is that we can't store the pieces of X transpose X that get summed across, or the final X transpose X. We might not be able to store that in memory. So the idea is, instead of doing the optimization in one step, of just finding the solution by knowing what the analytic optimum is, we're going to iterate through each of the coefficients in the regression, and we're going to do this as a coordinate descent. So in some ways you might think, well, that's not very smart, because as P gets bigger, yeah, maybe you don't need to store this huge matrix, but as P gets bigger, you're doing a huge number, you're iterating across a huge number of coordinates. So this could be very, very slow, and I'm not saying this is the world's best algorithm, but just as an illustration of something that you could do. So what am I doing here? Well, for linear regression, it's probably pretty obvious that if I want to find the optimum in one direction, holding all of the other beta coefficients constant, that's basically just univariate regression of the residuals after accounting for the other coefficients on the X that you're considering at the moment, the current covariate. So you can just write out beta hat as this equation here. Actually, did I get that wrong? So that should be Ri xi instead of Ri yi, sorry. And you'll notice something when we're thinking about setting this up as a MapReduce algorithm, that this sum down here is not a function of the current values of beta, whereas the numerator is. So I can pre-compute this sum down here outside of the iterations of my coordinate descent. So I just need to do that as a single MapReduce step. But then to compute, then I'm going to need to, but for when I'm computing the beta hat k's and updating them and going through the iterations, I'm going to have a loop over the coefficients, so over capital P, and then this is going to be an iterative algorithm. I'm going to have to loop over iterations to try and converge to the solution. So there's going to be a double for loop here. So let's see. So again, I'm going to set up, I'm going to use this map partitions, and I'm going to set up one matrix per partition to do this more efficiently rather than working line by line. And so I'm going to create this batches RDD. And I'm going to, this is just setting up a function that will compute the sum of squares of the x's all at once. So for each x in my regression, I'm going to compute the sum of that xk squared across the observation. So that's all this is doing. And then this function will calculate the numerator of my updates. So I'm going to calculate the denominator outside all of the loops. I'm going to calculate the numerator inside the loops, but I'm just setting up the functions that do those. And so the numerator is just taking the current residual but leaving out the contribution from the current coordinate that I'm considering, and multiplying by the x that I'm interested in, which is the pth one here. And I'm just doing a little trick here, which is instead of having to sort of deal with the bookkeeping of separating out the x that I'm interested in, I'm locally setting the beta for the x I'm interested in to 0 so that I can just sum across all of the x times betas. But this is basically serving to 0 out the one that I'm trying to estimate right now. And then so then outside of the loops I do the sum of x squared, which is computing in parallel the sum of x squared for all of the different x's. And I have to do a reduce, of course, that's just adding across the partitions. And then I have some initialization. One thing to remember is that if I have a NumPy array like this, I can't just say old beta. I'm going to sort of keep track of what the change in the coefficients is from iteration to iteration. But I explicitly need to do a copy of the beta because otherwise it's just a shallow copy and I'm just doing a pointer copy and I'll just overwrite the old beta value. So I'm going to have the beta and I'm going to have the previous value of beta. And of course, if you were doing this in any sort of non-trivial way, you would want to set up a convergence tolerance and you want to set up a maximum number of iterations and you'd want to do the optimization in an elegant way. For the sake of illustration here, all I'm doing is I just fix the number of iterations that I'm going to run and I just run the iterations, I run the optimization across that many iterations. So here's my double loop across iterations and across the covariates or the predictors. And I'm going to broadcast out the current value of the coefficients. I'm going to broadcast out the current coefficient that I'm interested in that I'm doing the coordinate descent on for that value, for that coefficient. And then I'm going to calculate the value of the numerator of the update, which is doing a map on this batches RDD, and obviously the reduction as usual is an addition. So then this is just the numerator divided by the denominator to get the new value for the pth beta, and then I just continue iterating. So obviously not a complicated optimization. And I don't think I will, since we're moving along in time, I don't think I'll take the time to run it here. If you actually watch this run, it takes a while. Each coordinate update takes 7 seconds, and then in this case, well, in this example, there were only 10. I'm still using that same regression where there are only 8 or 10 covariates, I guess 8. And so it takes about a minute per iteration. After 4 iterations, we get numbers that are reasonably plausible. This is the intercept, so the average delay, taking all of the covariates to be 0, is about 7 minutes. This is there's a positive coefficient with distance, so longer flights tend to have more delays, or tend to have longer delays. All of these are coefficients relative to the dummy level is Monday. So this is saying Tuesday is less delayed than Monday, Wednesday is about as delayed as Monday, Thursday is more delayed, Friday is even more delayed, Saturday is much less delayed, and Sunday is a little bit less delayed. And that's sort of consistent with the U.S. airline system, so at least we're getting something plausible. Yeah.
Is there a way to find out, this would be where those 7 seconds are going? I mean, what you're doing during those 7 seconds, why it's taking so long. I'm imagining, if you wanted to do an MCMC, 7 seconds per step is too long, and probably you're not spending most of it adding up the numbers. But is there a way to kind of diagnose these problems or figure out where you're spending?
Yeah, there's a variety of profiling tools. I'm less familiar with the Python profiling tools. I could get a list of tools and send that to you. Yep.
Yeah, I mean that's a good question. I would suspect in this case that it's basically doing the additions and the various calculations that it needs to do. But there may be a fair amount of overhead. I'm not sure. Okay, so that was coordinate descent for linear regression. That
Sorry, Chris, do you mean to say that if you had an empty reducer, it would go almost instantly, or if an empty mapper, it would go almost instantly? That is, if you weren't adding anything, you just return a number?
I think it would be pretty quick. Yeah.
Yeah?
Yeah. Yeah, my experience is that when I get fairly small partitions and there's not much being done to them, that a given task may come back in like 20 milliseconds or 50 milliseconds or something like that.
Yeah, and Spark is pretty efficient down to tasks that are lower, like about 100 milliseconds.
Right.
Anything that's much smaller than 100 milliseconds is hard to schedule. It's just like there's more overhead just in scheduling the job.
Right,
to
and
run.
saying, go do this. Like, oh, I'm done, go do this. But that's also an answer to Andrew's question, which is you want the partitions to be big enough that your operation on a partition is more than, say, 100 milliseconds in calculation time. So that's sort of another part of that trade-off. Okay, so that may not be, that's probably not a particularly good algorithm for fitting a big linear regression, but at least it gives you, a simple template that you could use that might be useful for other things. Another example of where you would use coordinate descent is doing the lasso. So there's a pretty well-known paper by Friedman et al. From a couple years ago in Journal of Statistical Software that basically is the algorithms behind the GLMNet package in R, and that's a package that will basically fit penalized GLMs. It might be fitting it with an L1 penalty, which is the lasso. It might be fitting it with an L2 penalty, which is, what's that called again? Ridge, right, thanks. I'm a Bayesian, I should know that, right? It might fit elastic net, so some combination of L1 and L2, so it has a variety of different penalties it accommodates, and it deals with GLMs generally. So in this case, I basically took one of the basic algorithms from that paper and implemented it. So that paper uses coordinate descent, and it provides a few different coordinate descent algorithms where it basically iterates over the coefficients. So what I thought I'd do here as an example is, again, I don't want to let p get too big because then I'm iterating over a very, very large p, and that's going to take a lot of time, so that this thing is not necessarily going to scale very well in that dimension. And maybe there are better algorithms for doing the lasso where you have a large number of covariates. I'm not sure actually. Does anybody know? Is there anybody in here who knows enough about lasso type models that if I had p of being 10,000 or 20,000 or 100,000, that what algorithm I would use in this kind of context? Huh? Yeah, actually, that would be a good. I don't know Lars off the top of my head, so I don't know how efficient that would be compared to this. But that would be worth looking into. Is looking into Lars. Yeah. Okay, so it may very well be that it's sort of an open unsolved problem. I don't actually know. Okay, so for this case, rather than using the real example, I decided to just play around with using a simulated data set. So I'm going to simulate a data set where n is fairly large, although not too large for this particular example. And I have 100 covariates, and I'm going to take 10 of them to be non-zero and 90 of them to be exactly zero, and then I'm going to apply the lasso and see if it recovers the sparse solution in terms of the covariates. And then just a comment that we have a penalty parameter for the lasso. Oftentimes you'll estimate that via cross-validation. In this case, I'm just estimating this for a single value of lambda. And there is a nice idea in a few different papers, including this Friedman et al. Paper, which is basically this idea of a warm start, which is you're going to basically compute the lasso regression coefficients for multiple values of lambda. And once you get the solution for a given lambda, you're going to use those coefficient values as the starting values for the next lambda. And so that will basically give you good starting values, and that'll improve the convergence of each of the solutions for each of any given lambda. So here I'm basically using MapReduce to create my simulated data set. So my n in this case is going to be 10 million, my p is 100, I have 10 non-zeros. Here are my true betas, this vector of 10 non-zero values. I'm going to then append on a bunch of zeros to that. And I'm going to basically then create my RDD that is in a distributed fashion has my x vector for every observation, and where I compute my y value as being x times the true beta plus just some random normal white noise. And in this case, I have a little flag that allows me to create the x's as being correlated with each other. So if I just generate them independently, then every coordinate of x would be orthogonal to each other, and that's a much easier optimization problem than if the x's are not orthogonal to each other. So I basically just put a little autoregressive structure in here where a given x is autoregressed on the previous x, where I'm sort of thinking of an ordering of the x's.
Is there a way to generate multivariate normal with not identity covariant matrix?
Well, if you were doing a Cholesky decomposition, I guess you'd then have to start thinking about, you'd need
So we
to.
have the independent and then we multiply with the.
Yeah, you have to think about whether it would work in terms of memory, in terms of how big these things are. But the usual algorithm for doing that, just in terms of linear algebra, is you've got sigma is U transpose U, where U is the Cholesky decomposition, and then U transpose Z for white noise Z is has covariance sigma. Okay, so I'm going to again do an sc.parallelize, just like I did with the simulation study for pi before. So I'm going to parallelize across n here, which is the number of observations, and then actually I probably should have, before what I did was sc.parallelize, and then I gave it this, and then I had a comma, and the second argument was the number of partitions, but here I'm doing a repartition. I think this is probably not a very efficient way to do it, and what I should probably have done was put the 96 in as the second argument here, and not had to do the repartition. But then to that original sort of data set, quote unquote, of the numbers 1 up through the number of observations that I want to have, I'm then going to do a map, and I'm going to apply this sim data function that will generate the x vector and the y for each of the for each observation. Okay, any questions about that? All right, so again, I'm going to then take the resulting data set, and I'm going to do a map partition so that I basically create one matrix per partition, and I can then do the calculations in a more efficient fashion in using that entire block of information instead of having to iterate through the individual observations as independent rows. So that is what is going on here. So I'm creating this batches lasso object, and basically if you go to the Friedman paper, the algorithm is stated there, and I just decided to basically implement it just as a very simple direct implementation of what they have there. The algorithm there assumes that your covariates are mean 0 and standard deviation 1, so I decided to just standardize the covariates directly using MapReduce here. So I'm basically going through and taking my data set, which is in batches lasso, summing up each column, so I'm summing for each of the x's, and then that's going to allow me to compute the column means, so the mean for each of the x's. Then I'm going to, once I compute that as a MapReduce here, I'm then going to, I basically have the column means collected back at the master. And I'm now going to distribute those back out to the workers, and I'm going to do a mapping where I basically subtract off the mean from each of the columns. So there's another map step here where I standardize in terms of the mean, and then I basically have to do the same thing to divide by the standard deviation. I first have to compute the sum of squares. I then need to do a reduce to sum over that, and I need to divide by n and take the square root. That's going to give me the standard deviations of the x's, the standard deviation of every column. I have to broadcast that back out to all the workers, and I need to standardize each of the columns by their standard deviation. So again, there's another whole set of a MapReduce step and then a map here. So at the end of the day, I now have my batches lasso object, my RDD, which is cached in memory, and now I can go ahead and implement this coordinate descent algorithm for doing the lasso. So the one I'm implementing here, if you go back to the Friedman paper, is what they call the naive algorithm. They present another algorithm that does a much better job of exploiting the sparsity in this problem, because when I'm thinking about the lasso solution, I have a bunch of betas that are zeros, and there are all sorts of efficiencies that I can gain from recognizing that and not doing redundant multiplications. But here I just decided to go ahead and just do the simplest one I could. So this is alpha being 1 would be the lasso penalty. It turns out I think it's a numerical stability issue here, that it's useful to subtract a little bit off from alpha equals 1. And then I'm choosing my penalty parameter to just be 0.5 just to fix it at something. So obviously you would, in reality you would make this, you would use different values of lambda, and et cetera, et cetera. So basically the lasso algorithm involves a step where you're basically updating a given coefficient fairly similarly to the linear regression coordinate descent, and that's what this get num batch is going to do. Is it's going to do the it's basically going to do the calculation of x times the residuals. So that's what this mat minus sum of xb is here. But then there's going to be some thresholding that gets done, and that basically is implementing the lasso part of it. So if you go ahead and look at the at what I'm doing here for the actual iterations, again, this is not a very good optimization. I'm just doing a maximum number of iterations. I'm just going to iterate over that. I'm iterating over the coefficients, over the different covariates. So I'm going to do a broadcast out of the current beta values, the current covariate that I'm interested in, which is p, and I'm doing a little bit of a sort of poor man's sparse algorithm here. I'm just saying which are the non-zero elements, and I'm going to exploit that a little bit in my I exploit that in my calculation of the residual times the x values up here. So there's a little bit of smartness here, but not too much. So what am I doing here? I'm getting this calculation basically of the covariance between the residuals and the x that I'm currently updating. I'm doing a reduction to sum over that. I'm collecting that back at the master. That's sum num here. And then my update of my beta is this thresholding function that I set up. And this is just being run on the master. There's nothing in parallel here. This is a very low dimensional calculation. And you can see it involves the alpha, it involves the lambda, and the current value, and this sort of statistic that I've calculated in parallel. And then I go through and I just do some bookkeeping to update the betas and which ones are still are non-zero. So I guess I've done a few examples where I sort of actually ran stuff. It might be a little bit boring not to run stuff, but on the other hand, all we're going to see is just tasks being completed and cycling through. So I'm not sure there's a lot of point in going through that. So are there questions about sort of the big picture of what I'm doing here in terms of the coordinate descent, or how I've set it up and what the different map and reduce steps are? Okay, so if I go through and do that, I get something like what I might expect, which is these are the coefficients. So the first 10 are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And if we go back to what the original true betas were, they were somewhere way up here. They range from -2 up through 1.5, where the sort of 4th, 5th, 6th values were not all that far away from 0. Okay? So remember -2 and 1.5. And now if we look at our estimates, we'll see that we do indeed identify that all of these out here are non-zero. The larger magnitude ones have gotten shrunk some towards 0. So the true value here is -2, -1.5, -1. The true value here is 1.5. And you can see for a few of the ones where the true value is actually close to 0, it's actually just gotten shrunk down to 0.
What would the lambda?
What's that?
What would the lambda?
The lambda was 0.5. Yeah, so this would vary depending on what lambda is. Oh, it does. Okay, I actually have never fit a lasso before, I don't think. So
Okay.
you have some intuition that
So
that's...
I think because the lasso kind of like, if everything was independent, it reduced the beta, the original beta by like 2.5 by the lambda parameter.
Mm.
So everything that's below 2.5 should be expected to be reduced.
Okay. Okay, and when I was looking at this, I ran it for about 5 iterations, and it seemed like it was getting fairly close to converging after that point. Each coefficient update took about 3 seconds, so a single iteration was taking about 6 minutes for p equals 100 here. So you can see this may not scale very well if you've got a large number of p. We could have implemented the more efficient algorithm. That probably would have helped some. But I don't necessarily know what you would do if you were wanting to do lasso and you had p of 50,000 or 1,000,000 or something like that. I don't know if does anybody know the literature well enough to know if there's a better state-of-the-art algorithm? No.
Maybe you do something beforehand to select something.
Right. Oh, actually, wait. I sort of already asked the question. You were saying, well, maybe we'll think about Lars.
But
Yeah.
another way is like you do OLS on like only 1,000 observations and pick like 1,000 best and then do this thing.
Oh, okay. Yeah. So you might think of this, and you might think of tacking together a few different algorithms and doing some selection first or something. Yeah. Okay. So there might be other sort of ad hoc ideas like that. Yeah. Okay. So then the last. Actually, I should hurry up. I'm running out of battery power here. So the last thing I thought I'd show you is just linear regression via gradient descent, and this is going to be more efficient. So we talked about linear regression where I was going to go through and update a single coordinate or coefficient at a time, and that wasn't going to scale very well with p because I'm having to iterate over the entire set of covariates as well as iterating over the regular iterations of the optimization. So the idea here is basically to do gradient descent. This is not going to be Newton-Raphson because I'm not actually computing the matrix of second derivatives, because if I tried to do that, if I have a large p, there would be a lot of computational cost in computing the second derivative matrix. So I'm not doing the optimization is not very smart here. I'm just going to basically head directly downhill based on the gradient. As those of you who know something about optimization know, that's not going to basically, if you were taking account of the second derivative information, you're going to converge much more quickly than you would using just doing simple gradient descent. But this this is probably not going to be, hopefully not going to be too bad, and it's going to should be fairly computationally efficient. So what am I doing here? All I'm doing is I'm basically taking the log likelihood of my regression problem, which in this case is just going to be the sum of squares, and I am taking the gradient. The vector gradient with respect to all of my covariates. So I have this, million or 10 million or however long set of, if I have this gradient vector that is as long as the number of betas I have, but I need to calculate that gradient vector, the contribution to that gradient vector for every observation. Okay, so again, it's going to be a MapReduce because I'm going to calculate the contribution to the gradient from each observation, and I'm going to sum across those, and I'm going to have done the gradient calculation in parallel. So again, sort of as I've already said before, I haven't been at all careful about thinking about what's a good step size to use. So I'm just calculating the gradient. I have a somewhat arbitrary step size, which is the alpha here. How did I? Okay. So what else was I saying here? Yeah, so you would want to do, if you were really implementing this, you'd want to be a lot more careful about this. You'd want to think more carefully about what the step size would be. You'd want to make sure that when you take a step that you don't go too far and that you haven't actually found a value of the objective function that's larger than the current value that you're at. You might want to do some backtracking if you get into that situation. So there's all sorts of things that you can do to be more careful about this gradient descent algorithm. But the idea here was I'll just do something very simple, and it shouldn't be too hard to extend this if you were going to make it a more sophisticated, more realistic optimization. So what am I doing here? It's not. I'm gonna choose my starting values in a slightly smart way, which is I'm not going to start at all zeros. I'm going to start my intercept at the mean of the observations. So that's sort of the very least smart, the very first step in being smart about this in terms of starting values. So I'm going to do that as a MapReduce step, is I'm just going to compute the overall mean of the observations. And then I'm going to define my gradient function that will operate on a given, again, I'm going to do this where I've created, for each partition, I've created a whole matrix of the observations. I'm going to do the gradient calculation on that entire matrix at once, using matrix algebra and using the NumPy linear algebra calls. So I've got a transpose in here. So this is basically just I've worked out what the gradient is for linear regression. Obviously, that's not very hard to do, and it's it's basically y minus x beta multiplied by the x's. So that's just implementing that. I do have a function here that will calculate the objective function, which in this case, of course, is just the sum of squares. So if I did want to check that and make sure that I was going downhill and do those sorts of things, then I can do that. And so then I'm setting up a little bit of storage so I can sort of keep track of the betas as I go through my iterations. And then it's basically what we've already seen. So nothing too different than we've already seen. But in this case, I don't have the loop over the coefficients. I'm just looping over the iterations. sort of a weird way to put it. I'm just doing the standard iterations without having that extra loop. And so my gradient calculation is just mapping each of my partitions, of the data in my partitions, which is a matrix containing the x vectors and the y's for each of the observations. I'm doing the gradient calculation by doing the map, and then I'm reducing by basically adding the contribution to the gradient from each of the different partitions, and that's going to give me the total gradient. And then my update is I take my current beta, I subtract off my step size multiplied by the gradient, where I do a normalization to basically calculate the average gradient, and that just trades off with the alpha. So, and then here I'm just sort of keeping track of how far I've moved from one beta to the next over the iterations. And I can obviously look for convergence by looking at how much the betas move, and also looking at how my objective function changes. So okay, so in this case, after 99 iterations, I've gotten down to this set of values. So I'm not actually at the MLE yet. I think when I did it for another 300 iterations, I was pretty close to the MLE, so it took a few hundred iterations. But I am, I'm getting at least plausible values for the coefficients. This is still distance, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, the effect on the departure delays. Okay, does anybody actually have a Mac power cord for me that I could borrow? Great, thanks. We got one here. Is it, perfect, yeah, that's what I need. And can I unplug whoever's black cord this is? Okay, so those of you who know a little bit about sort of working with big models and doing machine learning on big models may know that stochastic gradient descent is a fairly standard algorithm, and so there's a machine learning library for Spark that will implement some of these model fitting optimizations, and they're in this MLlib library. And my understanding is MLlib for a lot of things uses stochastic gradient descent. The basic idea of stochastic gradient descent is you do gradient descent like I was just saying, but you only calculate the gradient from a random subset of your observations at every iteration, and the subset changes across iterations. So the idea is that you should be able to do pretty well in terms of honing in on the minimum. You don't need to use all of your observations, you just use some of the observations, and sort of a law of large numbers helps you out. So I didn't actually show an example here, but it's basically just one line of code. If you have your RDD already set up with your data in it, it's not hard to then use. Another question, yeah, question.
What about loading our own libraries if we're going to do text processing like NLTK, that sort of thing? How would one go about installing that software across the cluster, or a Python module across the?
Yeah, that's a good question. I don't know if I have an example of it in here, but there is a little helper script that comes installed on when you use the Spark EC2 script.
Yeah.
It comes installed on the master, and it's basically a script that says, do this on every node, on every slave.
So there's like a little configuration file in the Spark EC2 folder with which I can sort of declaratively
if I remember
ask for some libraries.
If I remember correctly, it's under Spark / sbin / I think the script is Spark / sbin / slaves.
Okay, I thought it was something else. I thought it was root.
There may be two.
Yeah, I think there's a root, Spark, bin, and then, I guess we could just look here.
Yeah.
So, oops, Control Z. So, that's not what I was looking for.
Can you look under root Spark sbin?
Yeah.
Yeah, I think it's
the start and stop.
The Spark config.sh.
It should be the slaves.sh. will run something on every one of the slave nodes.
So what is that Spark config sh file then? Is that?
Not sure off the top of my head.
I think I was actually doing this when I was trying to play around with Spark R. So, oh yeah, okay. So yeah, this is the one that. Sorry, I forgot your name already.
Frank.
Frank.
Yes.
That Frank was referring to. So root Spark sbin slave.sh, and then you can basically run any command here, and that command's going to get run on the slaves. And if you need to distribute files to the slaves, you can do root spark ec2 copy dir, and then copy a given directory that you want to copy over to all the slaves. So between the two of those, you should be able to do any sort of systems administration that you need to do.
That's in the start or start-slave.sh or start-slaves.
I don't. It's in root spark sbin slaves.sh, and then the example code is in the sparkr.sh, which is in the repository because I was using it for some of the sparkr stuff. Okay, so yeah.
So slightly confused with respect to how Spark translates Python into whatever's underlying in it. So we're going to use something like an LTK. That's a Python library.
Right.
And if we install it on every Spark compute node, do we just, I mean, it's confused, like how would I assign a function to be called by that underlying library?
Well, you just call it from Python because you're running Python code. Spark is running Python code on objects that are being transferred back and forth between Java and Python. So it's not that the Python code is being translated; it's the objects are being translated.
So I just try to say like map function to use one of them.
Yeah, I mean I've used NumPy here, so you could use some other package. Does anybody know? I have a couple final thoughts. One is about uncertainty. So if you're, I'll put in a little dig against the computer scientists here. Maybe if you're doing machine learning, you don't care about uncertainty. But if you're a statistician, you care about uncertainty. Does anybody know for these large P problems if there are good algorithms for estimating standard errors and covariances?
Well, so I know of ways that you can do it for particular estimators. Like, so
Okay.
if you want to use influence curve-based variance estimations, you can. That works. That's like a really computationally fast way to get variance on like model, like AUC. Like I have an R package that does that for
Okay.
AUC, so you don't have to use bootstrapping to do a bunch of stuff.
Okay.
That's what I do. But if it's not for each estimator, unlike bootstrapping, you have to like derive the influence curve for each particular estimator.
Okay, right. So it's not
So
sort
it's,
of
like,
out
not
of the box. Yeah.
trivial, but if you can find like, if you care about AUC, you could use like my package, or you could
Right.
another thing.
Okay, I hadn't heard of that before. Is influence curve the thing to look up to, or are there other keywords to find?
Yeah, it's actually people say influence function, but my advisor says influence curve. So I guess it was like originally. Anyway, so either of those terms would work. And I mean, I could point you to some papers.
Anybody else have any other things they want to contribute on the front of uncertainty estimation? Yeah.
Maybe you can consider Lasso as a base with, double exponential classifier. Then the uncertainty estimates are kind of straightforward.
Well, I mean, I would love to do Bayesian stuff with this since a lot of what I do is Bayesian. But if I tried to do MCMC in this context, it might be pretty slow. So we'd have to think about maybe we could do variational Bayes. I don't know if variational Bayes gives us uncertainties or not. This is getting a little beyond sort of my knowledge of the literature. But certainly, yeah, there might be ways to take some of these problems, think about them in a Bayesian context, and maybe there are computationally efficient ways to use the Bayesian posteriors. Yeah.
Variational Bayes will give you posteriors that are polynomial. So you get them.
Okay, so just a few final comments. So a little bit here about if you wanted to run Spark just on your own machine to try things out. I think the drawback here is you need to get Hadoop set up on your system, which I think might be non-trivial. But
No, actually, if you just if you download the Spark downloads and you just unzip them locally, so Spark, you don't need to have HDFS installed. You just need to have a file system that can be seen by every node in your cluster. And if you have a cluster of one.
Oh, okay. I should have thought of that. Okay.
Yeah.
Okay.
So if you just
you'd have to read data in, not using the HDFS stuff I was doing, but read it in just from the file system.
Exactly.
Okay, that makes sense.
And it's totally cool doing that. So
Okay.
it's actually very easy to use. Just you unzip it, and you drop it down there, and you can start using it from there.
All right, I'll try and fix this so I'm not saying something that is not actually correct. And there are a few other things I'll just point out. There's Spark SQL that allows you to do SQL queries with RDDs. There's Spark Streaming that allows you to do sort of online calculations. And then I've been playing around with this a little bit in the last week, which is Spark R, which provides an R interface. I have the Spark R.sh here, which I was looking at but showing you before. We'll give you some code for basically setting up a Spark R on one of these EC2 clusters. And then Spark R.R will show you a little bit of demo code for doing a few basic things. I was still having some problems with some of the basic calculations and running into errors, and I was going back and forth with some of the AmpLab developers. So I'm hoping to put a little time into making this, the demo code that I have in here, a bit more robust and actually working in more cases than it is right now. But if you're interested in using Spark with R, then you might check this out. I suspect it would be a fair amount slower than Python, but you might be interested in doing that. And I guess the final thing I'll say is just I have a few resources down here, basically where I was getting this material from. There's the AMP camp that I mentioned last time on the 20th and 21st. I don't know if it's full yet. It does cost $600 if you can't get a free invitation in some way, but that's one possibility if you were looking for more training. And the other thing I just wanted to comment on was just that Spark is not necessarily what you want to use for any given problem, so it's not going to solve all of your problems. And if you have a data set where you have a machine with a lot of memory, or a machine that has a lot of disk space, you may be able to work on a single machine and code up what you need to do on a single machine. So, as you're thinking about what kind of tool you want to use for your given data set, it's worth thinking about a variety of different options that you might try and doing a little bit of benchmarking and seeing what will work. And oftentimes, if you do have a sort of moderately large data set of a gigabyte, 5 gigabytes, 10 gigabytes, like particularly if you're on the SCF, our cluster machines have 256 gigs of RAM. They can suck in a huge amount of data into RAM and just work with it in RAM, and that may be sufficient for fairly big data sets. Yeah, so I guess that's all I have to say. I'm happy to stick around for some minutes afterwards if people actually wanted to sit here and play around and try things and ask questions, and if they ran into trouble and wanted to get my input. The other thing is I'll try and leave up, for those of you who have the AWS accounts that I've set up, I'll try and leave that set up for at least a couple weeks. I'll need to monitor and make sure the credits aren't getting run through too quickly. And I don't want to leave it set up for too long because I need to sort of check in and make sure that people haven't forgotten to turn off their nodes, and it's just sort of a hassle for me to manage. So I'm not going to leave it up for months and months. But hopefully I'll be able to leave it up for the next couple weeks if you end up wanting to play around with it, and you're welcome to shoot me questions as well.
So. There's a linear algebra routine for distributed computing. Scala pack that you mentioned there, so can that do linear regression?
Yeah, there are distributed linear algebra packages. There's something called ScalaPack, which is kind of old now. There's some new stuff that people out of, like Jim Demmel out of EECS is developing that I think is going to leverage both distributed computing and GPUs, and I think is probably going to be pretty powerful. I don't know what stage of development it's in, and that's something I'm meaning to look into, like probably in the spring or next fall. I'll probably do a workshop on that stuff once I learn more about it. And there's also something called, for R, there's something called PBD, which does distributed linear algebra and distributed matrix operations in R across a cluster, and that's pretty far along, and I think is a pretty good package. So
there's also H2O, which is an open source machine learning, and they have a distributed GLM, and they actually have distributed random forest, GBM, and deep learning. Yeah, it's open source.
Great. Okay. Well, thanks everyone.
So I'm in slaves SH file.
Yep.
So
and as you're going out, if anybody didn't sign in, please do sign in. I just want to get a count of numbers and where people are coming from.
Here, I put it in that the
Oh, so if you do the slave
So I set up the
SSH,
cluster
you
with this
just run
command.
that, and then the command that you
I
run
had
on,
cluster
that'll
size
SSH
already
onto all of the machines that you have
the
in
export,
your
and I'm
cluster,
trying to
and
log
run
in.
that command.
I'm getting cluster doesn't exist or something.
Oh,
Yeah, you
okay.
can't
So I can
you can't do it in a separate shell because you need to have the Amazon credentials. I mean, did you start it in the shell?
I did start it on this on my shell on my
right,
but did you start it in this same terminal session?
Exactly.
I think it was in another.
Exactly.
Yeah, so
Thanks,
you
man.
need to
No, no
have
problem,
the
no problem.
AWS access key ID and the
I
AWS
do have
secret
that. Yeah,
access key.
they're all. I put them in the bash
Yeah, I'll
profile,
actually be.
so they're all.
Yeah.
So they're all here.
What's
Oh,
yours?
okay.
So
They're not doing that well.
Yeah, I've sort of run into this a couple times. Been a bit confused because sometimes it works fine and sometimes it doesn't. Yeah, so that's there. What
And
else
the-
could it be? So
the
you,
other file is there as well, and
But
So yeah,
I
I'm
want to
trying
start
to
teaching
get
this.
trying to get some more information into it.
Even
Oh,
if you
I'm
don't
in
have
another
a
folder.
Cluster
master,
weekend and ran through these exercises.
then this is here as well.
On this weekend.
right. Yeah, because that's.
They're all there, and I checked if the name is the same, and the name is the same as well. And we pay every time we instantiate the cluster, right?
Yeah, and in fact, and you need to be
shutting.
you need to be shutting it down.
Yeah. So that's why I didn't delete it and try to create it again.
Where am I here? Oh, I'm right there.
Like, because I'm trying to give them more instructions. And
And I guess that if I didn't have the credentials, it wouldn't instantiate the
I
cluster.
think I have to. I had to-
Right. Searching for existing cluster. So it seems like. Are we sure that?